Greetings everyone. This video presentation is about our thesis, which is titled as Machine Learning and Black Swan Events. I am Tasneem bin Ahmed and my other thesis groupmates are Lamia Tabassum and Proshinjit Dash. We have completed our thesis under the supervision of respected Mahbubul Alu Mujumdar sir. So before talking about the methodologies and working process of our research, I would like to talk about stock market crashes, what black swan events are, and how to predict those crashes. A black swan event is a rare and unexpected event, and it is very difficult to predict in the world of finance. These events can happen because of natural disasters, political events, or because of ignoring the chances of risks that may have potential of causing stock market crashes. Author Johansson and Sornet refer crashes as outliers, whereas another author, Emily Jacobson, refers crashes as drawdowns. Our study and work in this research is strongly based on these two ideas. From the financial crisis of 1987 to even the recent COVID-19 pandemic stock market crash that has devastated the world economy, black swan events particularly have caused significant disruptions worldwide. For example, we all know about the financial crisis of 2007 and 2008. At this time period, the US stock market faced heavy losses. There was another crash during 2015 and 2016 in US stock exchange, which is called the stock market sell-off event. These two events triggered and caused long-term crisis in the global economy. In early days of trade market, it was almost impossible to predict these issues, but through the growth of financial world and global economy becoming interconnected with technological advancements, machine learning was invented as well in the meantime. So stock market prediction is the act of trying to determine the future value of a company stock or other financial trade markets. The successful prediction of a stock market's future price could result into significant profit, as traders would be able to be careful beforehand about their decisions or predict when, why, and how to buy, sell, or hold their stocks. The main objective of our research is to capture and solve existing problems from datasets using the log periodic power law by implementing statistical and various machine learning tools such as neural networks. Our objective is to also analyze previous failures to determine parameters for future study. For this, we have collected data and processed those data. We have performed feature selection and fit those data into models. We also performed cross-validation and we did backtesting users' previous crash data of major crashes from different regions. We performed error measurement and compared those errors with the output of other models.
Greetings everyone, I am Lamia Tabassum and now I am going to talk about some of the methodologies that we used as part of this research. The first one is the log periodic power law model, or in short, the LPPL model. Proposed by Didier Sornet and Anders Johansson, the LPPL model paves the way to describe and detect financial bubbles and critical behavior of stock market index. A financial bubble is described as a period of time going from a pronounced minimum to a large maximum by a prolonged price acceleration, followed by a crash or a large decrease. Now, prior to crashes, the stock market index price time series can be characterized by LPPL model, a power law decorated with log periodic oscillations leading to a critical point that describes the beginning of the market crash. As we can see here, the stock market index price I at the time of bubble termination can be represented by this nonlinear generalized expression of log periodic power law, where TC denotes the critical time at which the crash has the highest probability. The symbol A denotes the expected lock price at the peak when the end of the bubble is reached at critical time. B denotes the amplitude of the power law acceleration, whereas C denotes the amplitude of the power law oscillations. To denote the degree of exponential growth, the symbol alpha has been used. And lastly, omega denotes the scaling ratio of oscillations, whereas phi denotes the phase or time scale of those oscillations. The occurrence of the crash is a biased random phenomenon which occurs with a probability that increases as time approaches critical time Tc. Thus, using this model, we only expect to find values of Tc which are generally close to but symmetrically later than the real time of the crash. Here, we attempted to predict stock price index trends using the log periodic power law model. Now, on to the next model. Decision tree is a supervised machine learning algorithm that performs a series of sequential decisions at each node based on a set of data features until conclusion is reached. Decision trees in machine learning can handle both categorical and numerical data and so can be used for building both classification and regression models. This algorithm can not only learn complex patterns from data but also is robust to noisy data. It nonlinearly maps independent variables to dependent variable and is generally used for classifying nonlinearly separable data. A decision tree structure consists of a root node, internal or split nodes, and decision or leaf nodes. Each node of the tree represents an attribute of the instance, and branches descending from that node indicate one of the possible values of said attribute. The top level node corresponding to the best predictor in a tree is referred to as the root node. Each test node then splits the data into further divisions from this node according to some set criteria. The discrete splitting function uses certain criteria such as information gain, Gini index, and so on to determine the best attribute to start with and split the training dataset. The feature based separating uncertainty from information regarding target feature is considered to be the most informative. Through splitting, different subsets of the dataset are created, with each instance belonging to a subset. The final subsets are called leaf nodes and the intermediate subsets are called split nodes. The main idea of a decision tree is to identify the features which contain the most information regarding the target feature and then split the data multiple times according to certain cutoff values in the features, rendering target feature values at resulting nodes to be as pure as possible. This search process for most informative feature continues until the final tree is a tree with decision nodes and leaf nodes, with leaf nodes representing a classification or decision. Now, in order to accurately predict financial index movements using decision trees in supervised machine learning using historical data and technical indicators of stock, after preventing look ahead bias by lagging values of the technical indicator, a clause column is added to data signifying daily returns based on adjusted close price of index. This class feature contains binary values for up and down, denoting positive return and negative return respectively. To predict the daily change of movements using these technical indicators by applying a machine learning decision tree algorithm to dataset, the dataset is first split into two parts for training and testing the data. The training data is then used to obtain information gain of features. After training, this decision tree algorithm is used on test dataset to acquire probabilistic trend knowledge. Linear regression is a statistical learning method which determines the relationship between independent covariates and the dependent output variable. Here, linear parametric regression models take the general form y to be equal to f of x plus epsilon, where y is the predicted output variable, f of x is an unknown function, and epsilon is the error term that is independent of the covariates. Now, different regression models use different forms of this function f. In linear regression, f of x is equal to beta naught plus beta 1 dot x. This parametric form thus reduces the problem of finding a relationship between the covariates or the independent variable x and the response variable y to only determining two coefficients, which are beta naught and beta 1. Linear regression makes an estimate of these coefficients, where such estimates are represented with a hat on the variable, as we can see here. Using this method, the values of these coefficients are determined based on given data. The graph of this equation is called the estimated regression line, where beta naught is the y-intercept, beta 1 is the slope, and y hat is the estimated value of y for a given value of x. This method is used when prediction of an outcome variable is needed based on the value of covariates.
Dear audience and panelists, I am Prosenjit Das. I will be talking about the data exploration part in our work, which is one of the vital part in our case, because from this part we will have the idea of how our model should work and what values should we need to assign to the parameters using in our model. All of our dataset analysis will be based on two theories. One is from Emily Jacobson, who has defined market crash as drawdowns in the 99.5% quantile. I'll talk about more on the drawdown later part. And the second theory from the Johansen and Sornet, who have defined market crash as outliers. I'll tell what outliers is in the later part. In this candlestick diagram, two things are need to be noticed. One is the shooting bar or hammer shape in the left side, and another one is the engulfing pattern. These two patterns indicate that the market will be lower trend very soon. In order to gain desired output, choosing dataset is a key factor. This correlation matrix here shows us correlation between any two datasets. High correlation 1 means datasets are behaving almost same, and low correlation of 0 means that datasets have no correlation between them. We have chosen 6 least correlated datasets to work with. These 6 datasets on the right side do not have correlation more than 0.5. The reason is to choosing least correlated dataset is to study more diverse market around the world. These are the time series plot of datasets we are using, and the right side diagram are showing daily fluctuation between the range of -2 and +2. We can measure how volatile the market are using these two diagram. This is the autocorrelation plot, which compare a dataset with its own lag version. If we see on the diagram, the lag day 0 means on the same day, and on the same day dataset having strong correlation of 1, which is obviously makes sense because dataset cannot be different on the same day. But if we consider lag day 1 to 6, we can hardly see any correlation of data. The histogram of daily returns here tells us the maximum of daily gains or loss lies between -5% to +5%. The large gain or loss more than 10% is very rare. We also call them as fat tails, and those fat tails indicate the high volatility of market in one day. From the frequency distribution of this histogram, we can measure how many times the return was less than -10%, that means -0.1. And there are the duration of drawdowns. Drawdown is how much the price fall down from its last peak point to the next lower point. To find the duration, we initially have to +1 as maximum price and -1 as lowest price. Then we compare and plot until we get the last lowest point. These are the frequency of all drawdowns. We can now tell that drawdowns loss more than 50% is very rare. So far we have got the duration and the percentage of changes. So now we can sort them and rank them easily. Here is the size. Here size of the bubble is duration, and the rank ordering of all drawdowns is showing by this plot. In the previous couple of slides, we have analyzed based on the drawdowns suggested by Emily Jacobson. Now we will explore data based on the idea of outliers suggested by Johansen and Sonnet. At first, we need to know what the outlier is. The outliers are nothing but the data points that are significantly differ from the other data points on the set. So here is the we will plot indicate the market failures, and these are also we will distribution. Here the outliers are identified using cross mark. The two diagrams here identify previous black swans based on the two theory I have been saying so far. Left side is based on the drawdowns, and the right side's diagram is showing the result based on outliers. We can see here that the Jacobson theory, which is based on drawdowns, is more successful to identify market failures. Now, before heading to the result analysis part, I want to talk a little bit about the F beta score we have used in our models. F score basically used to evaluate performance. There are two types of F score. One is F1, which is harmonic weighted mean of precision and recall. Precision means how many selected items are relevant, and recall is how many relevant items are selected. So other F score is F beta score, which apply additional weight to the value, to value one of the precision or recall mode. In our case, recall is more prioritized than the precision because we assume that a undetected crash has more bad effect than the predicted crash, which is not occurred yet. But the beta here is a positive factor, and a recall is considered beta times as important as precision is. So we have used this beta score to set our threshold. From the model and analysis part, Lamia has discussed about the log periodic power law, linear and logistic regression, and decision tree. I will now talk about the result we have got from the long short-term neural network and from the support vector machine. So here's the RNN model we have used. RNN takes the sequence of input, and the input is dependent on the previous cell's output. Regular RNN has a problem dealing with long-term data sets. To prevent that, long short-term memory LSTM was introduced. In that case, we do not only pass the output from the previous cell but also pass the cell state to the next cell. The benefit is RNN can now learn more complex price structure which regression cannot. But of course, there are other parameters to consider. There is two types of LSTM we have used. One is stateful and another one is stateless. In the stateless mode, after passing each one batch, configuration is reset. On the other hand, in stateful mode, the last output of hidden state and the cell state from the first batch is used as the input of next batch. So in our case, stateful performs slightly better than the stateless one. These are the market failures captured using RNN LSTM. And other model we have used is support vector machine. Support vector machine uses different kernel function to project input feature. I'm not discussing details about SVM here. In SVM, there are called a parameter called C parameter, which tells how much misclassified should be avoided. And these are some test case result based on the S&P 500 dataset.
Here, the decision tree performed very bad compared to the others model. We cannot still learn from the complex structure. In many cases, price do not show upward or downward trend before the crash happen. So thank you so much all. That was all about our work. Our results are still not perfect. There is still many scope to work on the study of complex price pattern. We'll continue to improve our result. Pray for us. Thank you.